Assalamu alaikum wa rahmatullahi wa barakatuh. Okay, I've already shared the slides. Let me take it to the presentation mode. So we're still on the momentum equation, and we explain the steps for drawing the momentum on the force diagram. Okay, so there are many applications of the momentum equation. Here we will look. Okay, we discussed this. Okay, yeah. This is a classification scheme for problems that are solvable by application of the momentum equation. You have basically two types: stationary controlled volumes and moving controlled volumes. For the stationary controlled volumes, you have jets and vanes, nozzles and pipe vanes, variable velocity. And for the moving controlled volumes, you have constant velocity and accelerating. There are some of the examples in the slides, but basically I will concentrate on pipe bends, okay? Because as civil engineers or civil engineering students, this is one of the examples that is so much applicable, okay? When you have a pipe bend and you need to, let's say, find the force needed to support the pipe bend, okay? And the analysis of the forces involved and all that, okay? So while there are examples of jets and vanes which you can just check, okay, and so I will concentrate on the pipe bends. So try to look at the examples on the jets and vanes. Okay, the principle is basically the same. Okay, the principle is basically the same, and more often than not, in this case, because you'll be drawing the force diagram, so you find yourself applying, the concept of equilibrium, the concept of statics, the concepts that you learned in statics, and that is why statics is a prerequisite to this course. Okay, so this is for the fluid jets. When you have a fluid jet and how to find, let's say, the tension in the cable here, and this is the example. You have a concrete beam poured, and we want to know the tension here. Okay, so the force diagram, the momentum diagram, and then apply equation of equilibrium. Okay, and at the end the tension is obtained. This is a vane, okay, which is a structural component as well. And these are the tips for solving problem using the vanes. And this is an example which is applicable to the vane. Okay, but like I said, I will concentrate on the pipe bends, okay, which is more applicable to the civil engineering students. Okay, here a pipe bend is a structural component that is used to turn through an angle. Okay, so you can see this is the angle. That's why it's a bend. Okay, uh, uh, connected to straight runs of pipe flanges, because more often than not, for whatever reason, you may not be able to lay pipe straight. Okay, there may be need to turn, so, and whenever you want to turn, you use the pipe bends. Okay, and they are connected to straight runs of pipe by flanges. Okay, these are the flanges, bolted flange. You can see it here, bolted flange, two places. Okay, so you put bolt and knot to tie it, and the same thing here, two places. This is the bend, AB. And the tips, for solving problems that involve the pipe bends here. Tip 1: let each momentum flow equal mv. Okay, m dot, because M is the rate of change of mass. Okay. So this is the momentum flow. Okay, rate of change of momentum. So this is m dot v, and for A and V. Okay, so momentum flow, and then you include pressure forces because you have fluid passing through. So the forces where the control surface cuts through a pipe, that is a pressure force. This we did before when analyzing the pressure statics. There is a pressure force at section. And the pressure force is the pressure times the area, but it will be at both section. And remember, pressure is always compressive. So you have to show the pressure force is always pressing onto the sides, okay? Pressing is always compressive, okay? And to relate the pressure, PA and PV, it is most accurate, it is most correct to apply the energy equation and include head loss, okay? Because the energy equation include the head loss, although the next chapter is where we will be dealing with the energy equation. Okay, in the next chapter, but we dealt with the Bernoulli equation where we assumed that our flow is non-viscous, that is inviscid flow. And for inviscid flow, we have very negligible energy loss due to friction. Okay, so for that, there is no energy, there is no head loss. Okay, head loss is negligible for inviscid flow, but for viscous flow, then head loss is not negligible. You know, when discussing the Bernoulli equation, we then explained that, you know, in a given flow, you have an area where the viscous effect is more pronounced, like the area close to the boundary where you have the boundary layer, okay? And away from the boundary, you have the viscous forces having minimal or negligible impact on the flow, okay? So this we explained so well under the Bernoulli equation in the previous chapter, previous two chapters, in chapter 4 or so, or 5. And then you try to relate the velocities VA and VB, apply the continuity equation, okay? And then when the control surface cuts through a support structure, like a pipe wall, flange, include the loads, okay? Include the loads caused by the support on the force diagram. So for instance, if you have a support, so you include the force, let's say Fx and Fy, okay? So let's look at this example where we will apply the momentum equation to a pipe bend. And the problem statement here goes, okay, a 1 meter diameter pipe bend shown in the diagram. This is the diagram, okay? 1 meter diameter pipe bend is carrying crude oil whose specific gravity is 0.94. So crude oil is dense, less dense than water because the specific gravity is 0.94. That of water is 1, okay? And with a steady flow rate, so we have the flow rate, 2 meters cubed per second. The bend has an angle of 30 degrees and lies in a horizontal plane. Okay, it lies in a horizontal plane. The volume of oil in the bend is 1.2 cubic meter, and the empty weight of the bend is 4 kilonewton. The empty weight of the bend is 4 kilo, meaning excluding the weight of the oil inside. But we can always find the weight of the oil inside using the volume, you know, times gamma. Okay. Assume the pressure along the center line of the pipe of the bend is constant with a value of 75 kilopascal gauge. Find the force required to hold the bend in place. Find the force required to hold the bend in place. Okay, so let's look at the problem and analyze all the components and see how we are going to proceed with the solution. Here you have the flow, okay? We're given the diameter and the volume, okay? This is a bolted flange and the angle of inclination is, the angle of the bend is 30 degrees and it is in horizontal plane. So define the situation. Here we have crude oil. The bend lies in a horizontal plane, meaning the weight will be acting vertically down in the z direction. Okay, the weight of the crude oil, okay, and the weight of the pipe bend as well. And we have the volume of the oil. We are given the weight of the empty weight of the bend, and we have the pressure along the center line, which is constant, 75 kilopascal gauge. Okay, so we have it redefined again. We have 2 points, point 1 and point 2, and we want to find the force to hold the bend stationary. Okay, and let's generate ideas and make a plan. Let's select because force is a parameter and the fluid particles accelerate in the pipe bend, so we select the momentum equation to analyze. And here we can sketch a control volume that cuts through the support structure and through sections 1 and 2, and then sketch the force and momentum diagrams. This is the force diagram showing all the forces acting, okay, on the pipe bend. Okay, this is the pressure force PA, the same pressure force acting, because we were told that it is constant. Okay, they will not cancel out because this one at this end is inclined to the angle of 30. So when it is resolved, it will have component in the vertical and horizontal direction. Okay, and then we have Fx and Fy, which is the forces for the support. Okay, this is just 2D. Okay, don't forget this is the horizontal plane, but we have Z direction. The weight W will be acting, directly perpendicular to the paper. Okay, because it will be acting downward in the Z direction, which is not shown here, because here we have used 2D, okay, X and Y. And then the momentum, this is the momentum flow, okay, in and out. Okay, the momentum flow is constant, except that the outflow, because of the angle of inclination, will have component in the X and Y direction. So now let's apply the concepts of resolution of forces in the X, Y, and Z direction. What we want to find is to find the force that is required to hold the bend in place, which is Fx, Fy, Fx, and Fz. Okay, so now analysis. Using these diagrams as guides, we write the momentum equation in each direction, and all we need to do is to resolve the forces in X, Y, Z. Okay, so in the X direction here, and we are applying the resolution. So the sum of the forces, because all we are doing is applying the Newton's second law of motion, that the sum of all the vector sum of all the external forces. Okay, the vector sum of all the external forces is equal to the rate of change of momentum. Okay, it's equal to the rate of change of momentum. Okay, so we are summing the forces and be equating them to the change in momentum, or summation of the change in momentum. Okay, so we have Fx here, and we have the pressure force here, P1A1, minus the resolved part of the pressure force on the other face, which is minus, okay, cos 30 because of the angle of inclination, and is equal to the change in momentum, which is the uh, uh, outflow, the output of the final momentum minus the initial one. The final one is resolved along the x direction. That's why we have cos 30. Let me take this away. Okay, and then we do the same thing in the y direction. Okay, Fy, vertical one plus the vertical component of P2A2 plus, okay, is equal to the vertical component of the final momentum, or the momentum in section 2, okay, which is pointing downward. That's why it's negative. In the z direction, we have Fz minus the total weight, which is acting downward. Okay, so we have 3 equations, and we can use these 3 equations to find Fx, Fy, and Fz. How do we proceed? We can find the velocity of flow because we have the flow rate. We have the discharge. The discharge is 2 meter cube per second, and we can find the area. So we can use Q equal AV to find the velocity of flow, which is 2.55 meter per second. And next we calculate the momentum flow. Okay, the momentum flow, which is the mass flow rate times velocity, which is rho qv. Don't forget m dot is rho v. Sorry, is rho q, and then you have v. Okay, and then here we can just substitute. This is the density of the, because we are given the specific gravity. Remember, specific gravity, it will be specific gravity, it will be density of the crude oil over density of water. Okay, so density of the crude oil will now be the specific gravity of the crude oil times density of water. Okay, so that is why here we're multiplying by the density of water, and this is Q that is given, and this is the area, the velocity. So we find the momentum flow. So this is the momentum flow. Okay, and then the pressure force is PA. We were given the pressure in the center line, which is constant, and the area we can find it pi d square. The diameter is 1, so the radius is half, which is 0.5. Okay, so this is the pressure acting, and then we substitute to find Fx. Simple. Okay, so we substituted, and this is Fx. Okay, and to find the moment minus here, it means it is in the opposite direction of the assumed direction of Fx. Simple. We assume Fx is going this way, so it means it is opposite. That's what the minus indicates. Okay, so momentum in the y direction, we take this equation B, to find Fy. Okay, and we have almost everything. Okay, here we find Fy. Okay, so we substitute and get Fy. It's also negative. Okay, and then in the z direction, we use the total weight, the weight of the crude oil plus the weight of the bend. We were given the weight of the pipe bend as 4 kilonewton, and to find the weight of the crude oil, we use the specific weight, which is what? Weight over volume. Okay, so we multiply the specific weight by the volume, okay, to get the total weight of the crude oil, and we can get this one, the specific weight, by multiplying with specific weight of water. Okay, using the same principle of specific gravity. Okay, which is S, which is now gamma of crude oil over gamma of water now. Okay, you remember chapter 2 under the properties. So now from here, and then we multiply by the volume, because we know the volume of the pipe bend. Okay, and the crude oil is occupying the whole volume, hence we add to the volume of the empty pipe bend, okay, to get W. And once we get W, we can simply get Fz. Okay, and then the force to hold the pipe bend is now given in vector form, Ijk. Okay, so this is Fx now, for the I, Fy for the J, and Fz for the K. Okay, so this is an example of the application of the momentum equation. I hope it is clear. And here we will move on to the next chapter, which is on the energy equation. We have already started discussing about the energy equation partly under the Bernoulli equation, but now we will expand. Okay, any question? All right, now, no, okay. There's no question there. Let me share the next slide for the energy, which is chapter 7 now. Don't forget, I have a backlog of 2 weeks of lectures, and I will still find time to do it before the final exams. Okay, before the last day of the final lectures. I will try to find time and then produce them gradually. Okay. And tomorrow there will be quiz, okay, which will cover the Euler's equation. Okay, that is one, and then okay, I will explain tomorrow. So the energy equation. Here we will learn how to explain the meaning of energy, work, and power, and describe various types of head terms, which we did before, but here will include pump head, turbine head, and explain the meaning of pump, turbine, efficiency, and head loss. Okay, and list the steps to derive the energy equation. And we'll also sketch the energy grid line and hydraulic grid line, which we did before, but now we will incorporate the head loss in the uh, sketch of the grid lines. Okay, so now the energy equation. Here you have a dam, okay, you have a penstock, which is a pipe delivering water, huge diameter pipe. And here you have a powerhouse, for hydropower generation. Here you have a turbine, which is utilizing the power of the water coming down this height. Okay, we are just talking about momentum. You can imagine the momentum possessed by water, moving down this height. Okay, so it has high momentum, okay, and energy. Okay, so that energy is used to turn the turbine, which is connected to a generator that will be producing electricity to power lines. Okay, and then you have the tailwater where the used water is now disposed of. Okay, so the energy equation can be applied to hydroelectric power generation. In addition, the energy equation can be applied to thousands of other applications. It is one of the most useful equations in fluid mechanics. Okay, it is simply like the statement of the conservation of energy. Now, just some review on what energy is, which you must have done also in Physics 101. Okay, so energy is the property of a system that characterizes the amount of work that this system do on its environment. The amount of work that the system can do on an environment. Okay, so energy is simply weight times distance. Okay, weight, energy is weight times distance. And work, which is similar to energy in a way, work is done on a system when a force acts on the system over a distance. When you are standing and holding a weight, when you don't move through a distance, even though you have weight and you possess, energy, but you have done zero work because the force applied has to move through a distance. Okay, it has to move through a distance, and that is why the unit of energy and work is the same. This is weight times distance, okay, which will give you the unit of weight is Newton, distance is Newton meter. Here also force is Newton and distance is meter. So Newton meter. So they have the same unit, and the special, this is the derived unit, and the special unit is joule, capital J, which is the name of the scientist that has contributed, immensely in the development of the energy principle. Okay, joule. Okay, so so you either use joule or Newton meter. These are the SI unit of work or energy. Now, what is power? Which is the rate of doing work? Simple, rate of work or energy. Okay, so power is the quantity of work or energy over interval of time. Okay, so power is the quantity of work over interval of time. So what is the unit of power? The special unit of power is watts, capital W. Okay, and then you have the derived unit, which can be obtained. This is Newton meter. Okay, and time is what? Second. Okay, so meter per second is what? Velocity. Okay, so That's why power can also be described as force times velocity, because Newton is force, meter per second is velocity. Okay, so that power can also be expressed as the product of force and velocity. Okay. If I express it as the product of force and velocity, it doesn't mean that for a body to possess a power, it must have velocity, meaning it must be in motion. No, quantity of work can be energy. That energy can be potential energy, which is the energy possessed, by bodies due to their position in a field. Okay, so it can be static and yet possess power. So the energy equation. What effect does pumps and turbines have on the energy of a system? We will discuss this here. Okay. As we all know, a pump is a machine that is used to provide energy to a flowing fluid. Specifically, the pump increases the pressure of the flowing fluid. Okay, it increases the pressure of the flowing fluid. And once it increases the pressure, then the energy is going to increase because pressure is proportional to energy. Okay, pressure is a function of energy. If you remember the Bernoulli equation, you have pressure term. Okay, so examples of pumps include the piston pump, the centrifugal pump, the diaphragm pump, and the gear pump. All of these are examples of pumps. Pumps add energy to the system. Pumps, they add energy to the system. Okay. While turbine is the reverse, it subtracts energy from the system. Okay. A turbine is a machine that is used to extract energy from a flowing fluid. Okay. Examples of turbines include the horizontal axis wind turbine, the gas turbine, the Kaplan turbine, the Francis turbine, and the Pelton wheel turbines. They all uses energy of the system. They extract energy from a fluid, okay, and use that energy to rotate a shaft, which is connected, let's say, to an alternator, to a generator, where electricity is generated, okay, as a result of the mechanical movement of the turbine, okay. And a pump transfers mechanical energy to a fluid by raising its pressure. This I mentioned. It raises its pressure. Okay, and a turbine extracts mechanical energy from a fluid by dropping its pressure. So you can see a pump raises the pressure of moving fluid, while a turbine extracts mechanical energy from a fluid, thereby dropping its pressure. Okay, because when you extract mechanical energy, remember the Bernoulli equation is simply like a statement of the conservation of the mechanical energy of the flowing fluid. So when you extract mechanical energy, basically you are reducing the pressure. Because you remember, you can express the Bernoulli equation in pressure form. Okay, the flow pressure, or using the static pressure plus dynamic pressure, plus the hydrostatic pressure. So note that pressure, which is Pascal, which is the SI unit, special unit, or joule per meter cubed, okay, or joule per meter cubed, okay, itself is not a form of energy. So pressure and energy are not equal. I mean, you cannot say pressure is equal to energy. No, pressure is not a form of energy. Rather, it can be thought of as a measure of stored potential energy per unit volume. This I explained before when I was explaining pressure. I think it's in chapter 4. Okay, it is the stored potential energy per unit volume. That's why the unit of pressure, Pascal or Newton per square meter, can also be expressed as joule per meter cubed. I explained this very well before. Okay, it's a measure of the stored potential energy per unit volume. Okay, and we live in a perfect world where energy is fixed with time and space? No way. But energy cannot be lost. Okay, it can only change from one form to another. Okay, it can change from one form to another. So the total, do we live in a where energy is fixed? Energy may be in a way fixed, but it changes from one to another. Okay, but the total energy of a system remains constant. Now, concept quiz. Here It says, according to Bernoulli equation, what is the total head at point 1 and at point 2? Okay, what is the total head at point 1 and at point 2? Okay, the the difference in elevation is simply, this is 20 meter, this is 100, so the difference in elevation is 80 meters. Okay, so what is the total energy? According to the Bernoulli equation, there is no loss of energy. So the total head at point 1 is given by this, which is the piezometric. This is the piezometric head plus the velocity head, and this is for the second point. Okay, and this is the pressure head at this point. Okay, if the elevation is the same, so it cancels out. So, and if we assume the velocity to be constant, okay, if we assume the velocity to be constant throughout the pipe, okay, so the total head will be the same, will be maintained even at point 2. Okay, it will be the same. There is no loss of head. Okay, although here, as it is flowing, because the velocity here is almost 0 compared to the velocity here, so we can look at the velocity head. Okay, the velocity head. So we have the pressure head and the pressure head and the velocity head. Okay, the pressure head as well as the velocity head. So here we may have like pressure head, okay, and then the velocity head. But in this case they will be parallel. Okay, if we assume the Bernoulli equation, because there is no loss in head. Okay, so the difference between this is the velocity head, v squared over 2g, and this is the pressure head. Okay, and the sum of the two gives the total head. Okay, as we are going to analyze later, this is usually not the case, because as it is flowing, you know, more often than not in pipe flow, you may not be able to neglect viscous effects. Okay, as such, you will have head loss due to friction and other minor losses, as we are going to explain. Now, the energy equation, what is the energy in this system? Okay, the energy, as we have mentioned, is weight times distance, and which is simply weight times head, because head is simply height. Okay, simply, or distance is also simply, can also be expressed as height. Okay, so weight times head. Okay, so head is simply energy per unit weight. Okay, head is simply energy per unit weight. So we have been mentioning pressure head, okay, elevation head, you know, all this. So it's simply energy per unit weight. Okay, energy per unit weight. Okay, that is what we call head. Okay, and head can be thought of as the ratio of energy to weight for a fluid particle. So head is also a measure of the energy in the system. Okay, it's a measure of the energy content of the system. Now, we already explained, you know, this is the flow energy. Okay, this is due to this is the pressure head due to the flow energy. This is the elevation head due to the hydrostatic energy. This is the velocity head due to the kinetic energy. Okay, this is due to the kinetic energy, and Z due to the potential energy, and the pressure head due to the flow energy. This we analyzed before, you know, under the Bernoulli equation, using the energy form of the Bernoulli equation. So we are simply saying that the energy per unit weight at point 1 is equal to the energy per unit weight at point 2. Okay, or simply the energy content at point 1 is equal to the energy content at point 2, meaning the energy remains the same. That's why we said it's more or less like a statement of the conservation of mechanical energy of the system. So what is the energy in this system? Okay, at point 1 and point 2. Okay, so the sum of the pressure head plus elevation head plus velocity head. Yeah, if we take this as we can, no, this has if we take Z2 to be the reference, so this is now 0, but Z1 is equal to the difference in elevation, which is 80. Okay, Z1 is 80. Okay, which is the uh, head. Okay, and you have the pressure head and the velocity head. Okay, which will be when you add uh, them up here. No, yeah, here, sorry. If we take this to be the elevation, okay, like I explained before, this will be parallel, meaning the total head at point 1 given by this equation is equal to the total head at point 2 given by this equation. Okay, the total head remains the same, meaning the sum of the elevation head, pressure head, and velocity head remains constant. Okay, it remains constant. But as we are going to see later, there is loss of head. Okay, uh, it is expected that if it remains constant, when you put a piezometer at this point, okay, water will rise up to this level, isn't it? If the pressure, but in real case, it will not rise up to this level. Maybe it will rise up to maybe this level, let's say. Okay, then what happens to why the difference? It means it has dropped. It has dropped, from this to that level. So what accounts for the drop in the uh, pressure head? Okay, what accounts for the drop in the pressure head? That is accounted for by the velocity head. Okay, if we assume the Bernoulli equation applies, so we can assume all this represent the velocity head. But then, as we are going to see later, that again, as the water is flowing, it is losing head. Head in form, it is losing the pressure head. This is the head loss, okay? This is the result of the head loss. You can see the head here is up to this point. When you put a piezometer, the head is supposed to go up to the height of the water in the tank here. But there is head loss, which is the difference in head here. That is the head loss, okay? So that is accounted for by the velocity head as well as the head loss due to friction and minor losses, which we are going to explain, okay? So for ideal condition, it remains the same, okay? For for ideal condition, we it remains the same, okay, meaning we will have the pressure head plus the velocity head remaining at the same height as this height, okay, without the head loss. Okay, now the energy equation. This is the energy equation in which you have the pressure head at point 1, the total head at point 1, pressure head plus velocity head plus elevation head plus pump head. We mentioned that pump adds energy to the system. Okay, it adds energy to the system. So if there is a at the head provided by the pump, okay, which is the pump head, and then here we have, a pressure head, velocity head, and elevation head. plus turbine head, if we have a turbine, because a turbine extracts energy from the system. It extracts energy from the system, and then plus head loss. If we don't have turbine head or pump head, we strike them out, but we always have head loss. Okay, so the energy equation takes care of the actual situation that occurs, while Bernoulli equation is more or less like an idealized form, okay, of the conservation of energy. Is an idealized form, while the energy equation takes care of additional inputs such as pumps, turbines. Whereas if you have a pump, you cannot apply the Bernoulli equation before and after the pump, okay, because the pump supplies head. If you want to use the pump, to analyze, if there is a pump in your system and you want to analyze the flow in the system, you have to use the energy equation. Okay, so here when you bring this term, this is the energy at point 1 minus energy at point 2, which is the change in energy. So there is change in energy because of this. This is the turbine head minus the head provided by the pump plus the head loss in the system. If you don't have a pump or turbine, this will all be zero. Okay, and then but you always have head loss. Okay, so the change in energy between point 1 and point 2, the difference between the change in energy between point 1 and point 2 is accounted for by the head loss. Okay, and if you have a turbine, you include it. If you have a pump, you also include it. We'll take example where to demonstrate the application of this equation. Okay, and here you see we have alpha 1 and alpha 2. Okay, these are the what we call the velocity correction coefficients. Okay, here we use the average velocity. We assume the velocity is constant, and we always it will only be constant for uniform flow. And uniform flow usually doesn't occur in a long reach of pipeline or in a long reach of our channel. Okay, so more often than not, we have to use the average velocity. To use the average velocity, we have to use the correction factor for the velocity, which is alpha. It's called Coriolis coefficient, okay, which is the correction factor for velocity. But for most probable problems, we assume that it is equal to 1, okay? But sometimes it has a value less than 1, because the average velocity is usually, as we have seen before, is less than the maximum velocity. Okay, it's less than the maximum velocity. It's like the average velocity of the velocity profile. And yeah, okay. Now, still on the energy equation, is the head loss, head removed by turbine, and this is the head added by pump. Pump always add any head or energy, and turbine always removes head. Okay, and thermal energy here refers to the energy contained within a system that is responsible for its temperature. Okay, the energy contained within a system that is responsible for its temperature. And heat is the flow of thermal energy. Okay, heat is the flow of thermal energy, and thermal energy is the energy contained within a system which is responsible for its temperature. Okay, you always hear of a body being cold, like now we are starting to experience the cold weather. Okay, temperature is going down, so you talk about cold temperatures. That is because of the thermal energy, the heat flow. Okay, the heat flow or the flow of the thermal energy is low in that case. Okay, and head can be thought of as the ratio of energy to weight. This we explained before for a fluid particle. Or head can describe the energy per time. Okay, the energy per time that is passing across a section, because head and power are related. Okay, head and power are related. This is the relationship. Power is equal to the mass flow rate times GH. Okay, mass flow rate times GH. So this is a relationship between head and power. And then head loss is the conversion of useful mechanical energy to waste thermal energy. You convert the mechanical energy from the flow energy, the kinetic energy, the potential energy to waste thermal energy, okay? Because the head loss here we call HL, okay, is the as a result of the conversion of the mechanical energy to thermal waste thermal energy that cannot be utilized for any meaningful purpose. It is waste because it cannot be extracted and utilized, okay? But is converted to waste thermal energy as a result of what? Frictional heating. Because as it is, just try to rub your hand, rub your two palms, you'll begin to feel some warmth, some heat being generated. Okay, so the same thing when fluid is flowing, when you have any two bodies in contact, there is frictional force. Okay, there is frictional force. So head loss is simply the conversion of useful mechanical energy to waste thermal energy as a result of frictional heating. And this manifests itself as a slight rise in the temperature of the fluid. Okay, so if the temperature of the fluid at this point, it will be measured, and then 2 kilometers down, when you measure the temperature, you realize the temperature are different, because as the fluid is moving, it is experiencing frictional heating. As it is moving, it is experiencing frictional heating, okay, as a result of the conversion of the useful mechanical energy to thermal energy. And thermal energy is what is responsible for the temperature of the fluid. So for that, because of the head loss here, you realize that here you have like the velocity head, okay, and then you have the head loss here, HL, and this is now the velocity head, okay, the velocity head. So meaning when you put a piezometer here, water will rise up to the level of the piezometric of the pressure head, okay, which is to this level, okay, because of what here. But when you put pitot tube, when you put a pitot tube, you remember we did pitot tube, when you which measures both the static pressure, that's the piezometric, the pressure head, and the dynamic head, it will rise, water will rise up to this level because the pitot tube measures the velocity head, okay, it measures the velocity head, but water will never rise to the initial level, which is this, because of the head loss, okay, because of the head loss. So, and head loss is simply the conversion of the useful mechanical energy to waste thermal energy because of frictional heating. As it is flowing, you realize the temperature is slightly raised as it is flowing because of the head loss. So these explanations are very, very important and vital towards understanding why do we have head loss. Okay, why do we have head loss? And here you have like a controlled volume in which you have, you know, pumps, energy inflow. So energy into controlled volume by flow and pumps. Okay, and this is the energy out of controlled volume by flow, turbines, and head loss. Okay, turbines extract energy. Okay, and this is by flow, and this is by head loss, because as it is flowing, you will always have head loss, and the head is lost because this is the head form. Basically here we're talking about the pressure head, because if the velocity is literally constant, it is the pressure head, so the pressure head will be dropping, so the head of the pressure head will be reducing, okay, and that is the head that is lost. And why does it become lost? Because of the uh, conversion of useful mechanical energy to waste thermal energy as a result of frictional heating, okay, which reflects itself as a slight rise in the temperature of the fluid. Okay, this is very, very important. And due to the time factor, I will stop here. And then tomorrow we'll continue with the total energy equation, which is something that I presented before, okay, when explaining the Bernoulli equation. Again, we'll explain it here, but here we will include, you know, the uh, also look at the head loss, okay, the head loss factor, and then we'll look at some examples. So any question? Okay. If okay, if you don't have any question, then we'll see tomorrow. Okay, we'll hold our a quiz tomorrow as well.